This conference will now be recorded.
Hello, this is Miss Metzger, and I am sorry to get this to you guys so late. It's been a crazy day and a half. So I'm doing some of the extra problems from the Brief Calculus Test 2 video for the review for the test. I had a couple requested ones, plus I'm trying to do kind of one of each type for you guys so that you can just check and see if you're doing things correctly as you're studying for our test. So I'm going to start off with number 6 because we kind of did most of the first page together in class the other day. So we're looking at a retail sporting goods store estimates that weekly sales S and weekly advertising cost X are related by the equation S equals 2,250 plus 50x plus 0.35x squared, and the current weekly advertising costs are $1,500, and these costs are increasing at a rate of 125 per week. Find the current rate of change of weekly sales. So the most important part about this problem is noticing what are the variables and what are the dx dt's or dy dt's. So when you look at because the formula is pretty much what we're going to just take the derivative of. When you look at this right here, notice it's just the advertising cost. That's a singular unit of measure. So that means this is kind of going to be our X. The other thing they gave us, they said it was a cost that are increasing at a rate of 125 per week. Notice that's a rate of change for the cost. So that's dx over time because it's per week. So dx dt. So we now know that when we go to take our derivative, 1,500 is going to stand for X, and the 125 positive, because it's increasing, is going to stand for dx dt. So we're going to be taking the derivative of this function with respect to time. So I'm going to write this again over here. And we're going to take this, remember, with respect to time. So change in sales over change in time, because the derivative of S is 1, but we have to chain on the ds dt. Derivative of a constant is 0. Derivative of 50x is 50, but we need to chain on the dx dt since we're taking our derivative with respect to time. And then this would be 0.7 when we times that together, and that would be x to the first. But then because it's not a t, we chain on the dx dt. So we're essentially just working this out as 50 times the 125, because that's the dx dt, plus 0.7 times the 1,500 times the 125 again. So we want to get our calculator and we want to work this out. So that's going to be 125 times 50 plus 0.7 times 1,500 times 125. That comes out to 137,500. Remember, this is dollars, and it would be per week, just like the rest of the problem was. So we need to write that out using our units. And hang on just a second. I am making sure my pen's good. So 137,500, and that would be our weekly sales. So per week, sales per week, if we want to be very specific. In sales, there we go. All right, so number 7 works kind of similarly to this. You're going to be doing, the dc dt, dp dt, or dr dt, and you can find dp dt using that. So let's move on to our next one. Let's look at number 8. 8 is a different type of problem. So on this one, it says use the graph to estimate the open intervals on which each function is increasing or decreasing. So that means we're looking for when are we going uphill versus downhill. So when you're looking for open intervals, that means you're going to be reporting these x values to us. What are the x values that these things run through? So if you look right here on this first one, this is decreasing. See how this is going downhill from negative infinity all the way till we get to that point right there on the x-axis. So that's going to be decreasing from negative infinity to -3. And then the graph starts going uphill from -3 to here. Because we have a max here, that means it's going to start going downhill again. So I'm increasing from -3 to 0. So then when I start decreasing again, I do that from 0 to 3. That goes with this range. And then I'm increasing again from 3 to positive infinity. So union that with this one. This one's a little harder for students because the nice thing about this one is that the changing point was at the x-intercept. Here, you're looking for where's the max and where's the min, because those are places where you can change from increasing to decreasing. So on this one, we have increasing, so we'll use yellow again. So we're increasing from negative infinity to whatever this point is right here, which we're going to have to estimate. Then we're decreasing. And then right here, wherever that point is, that minimum, we're going to increase again. So we have 2 increasing regions and 1 decreasing region. So let's write this down. And you have to estimate what these are because there's no exact points here. So I think she did like negative 1.6 because it actually is a little bit more towards that. So we'll say that we were increasing from negative infinity to negative 1.6. And again, if you put negative 1.5 or negative 1.7, I'm going to give it to you because there's no defined point there. It's just estimating. And then we also union that with this, which may be 1.6 or 1.7. So 1.6 to infinity, keep it consistent. And then we were decreasing in the middle of that, so negative 1.6 to 1.6. So when you ask someone to use open intervals to describe increasing, decreasing, you're describing the x values where I'm either going downhill on the graph or uphill on the graph. Okay, let's look at number 9. It says a fast food restaurant determines the cost and revenue models for its hamburgers. So they've already given me the 2 formulas. If it was me, I would probably take this one, this second one, and I would distribute that 1 over 20,000 and write everything as decimals because the first one had decimals. So 65,000 divided by 20,000. Oop, too much. That is 3.25. So R is 3.25x. And then what is just 1 divided by 20,000? That is point, and there's 4 zeros and then a 5. So minus 0.00005x squared. So that's another or easier way to write the revenue function. So it says write the profit function for this situation. So we need to do revenue minus cost. So profit is revenue. That's a 2, which is this formula, minus cost, which is this formula. And that's going to be profit is, let's see, we'll put the squared part first. So negative 0.00005x squared. That is 3.25 and then minus 0.6. So that is 2.65 positive x. And then we have to subtract that 7,500 because we have to distribute that negative. So there's my profit function. So that's part A. Determine the intervals on which the profit function is increasing and decreasing. Remember, that has to do with first derivative. So we need to talk about P prime. So P prime would be, that's going to be what? Negative 0.0001x plus 2.65. We'll solve that set equal to 0 to find where the critical numbers are. So that would be, let's actually just go ahead and, I don't have a lot of room, so let's just write this. I would go ahead and add that over, so that's going to be 0.0001x equals 2.65. And we're dividing 2.65 by that 0.0001, which is 26,500, which is hamburgers, because this is, remember what they're making, and the x, and that is between our domain. So that is possibly a good answer. And then we would test to see if it's increasing, decreasing on each side. Now, if you want to make your life easy, just pick 0 on the left and 50,000 on the right, because those are our max and min of our starting and ending values. So if we plug those into P prime, that'll tell us if it's increasing or decreasing. So if you plug in 0, you get a positive 2.65. If you plug in 50,000 and times it by this decimal, it actually ends up being bigger than 2.65 and negative. So it ends up being negative, which means this is a max because it goes from increasing to decreasing. So that actually is the answer to C part as well. How many hamburgers do they need to sell to obtain a maximum profit? 26,500 hamburgers. So the increasing, decreasing intervals were from 0 to 26,500, we were increasing, and we were decreasing from 26,500 to 50,000 because that was our domain. Okay, so we're going to be looking at number 10 next. Oh, and by the way, you can put they did this in the key. Because this was equal to on these, you can put closed intervals on those endpoints because it is actually, it is a 0 to 50,000. All right, so let's look at number 10. It says find the critical numbers of the following function. I didn't do A because that one's just you take the derivative, it's quadratic, and then you factor it and you get two answers. I wanted to do B since it was a fraction one. So remember, we have to take the derivative of this to figure out if it has critical numbers. So we need to do the quotient rule here. So the top function is 7x, the derivative of that is 7. The bottom function is x plus 1, the derivative of that is 1. So remember, we do our diagonals. So 7 times x plus 1 minus 7x times 1. So this is for g prime of x, all over x plus 1 squared. That would be 7x plus 7 minus 7x over x plus 1 squared. And that ends up just being 7 over x plus 1 squared. Now remember, when you look for critical numbers, you check what makes the top 0 and what makes the bottom 0. There's no x's for the top, so there's no critical numbers up top. This would be equal to 0 when x is -1. This is not a critical value though, because the original function was undefined at -1. Pen's going a little crazy, sorry. So you cannot have a critical number be a max or min if the function does not even, it can't even be a critical number if the function does not exist at that specific point. That means there was an asymptote there. There is no graph there. It's a dotted line that we never cross. So this has no critical values because the only value we had down here when we did the first derivative was undefined in the original function. So we put no critical values. Okay, so let's talk about 11a, find all relative extrema. So that means we want to take the first derivative, find the critical numbers, and then we actually want to do the increasing decreasing test to see if they're maximums or minimums. So I picked A just because it's a different derivative to take. This is another quotient rule. This is just a polynomial. This one is using the chain rule. So we have to do the derivative is 3 times 4, which is 12, times x squared minus 9 to the, I don't know why my pen's doing that, to the second power, but because the inside has a derivative, we have to chain that along. So that's going to be a 2x. So this is actually 24x and then x squared minus 9 squared equals f prime of x. Okay, so we set those equal to 0. So 24x equals 0 would just be x equals 0. X squared minus 9, even though this is squared, that ends up being an x plus 3 and an x minus 3. So we get -3 and 3. Oops, there we go. So we want to test those on our number line to see if they're increasing or decreasing around them. Now, if your function, remember, comes out in the test and you get increasing back-to-back or decreasing back-to-back, that means it's not going to be a maximum or minimum. Usually that means it's a point of inflection. So let's just see what happens. So we put -3 here, 0 in the middle, and then 3. We would pick -4, -1, 1, and hang on just a second. My pen is really going crazy. 1 and maybe +4. Plug those into our first derivative. So go back up here. I would probably plug it into this one. So 20, and if you need to, just plug it into your calculator. If we square -4, that's 16, minus 9 is 7. 7 squared is 49. Then we times it by the 24 and by the -4. That ends up being a negative overall. So this region is negative. If we plug in -1, that would be -1 squared is 1, minus 9 is -8. -8 squared, though, is 64. times the 24 out front times a -1. Notice that region is also negative. That means this is not a max or min. This is most definitely going to end up probably being a point of inflection if it exists there. And then for 1, we get a positive when we plug in, and for 4, we also get a positive. So essentially what happens here is we have 2 places where we don't change our direction. We kind of get that x cubed situation where your graph is continually going up, but it kind of momentarily flattens for a second. So the only real extrema is the one where you change from decreasing to increasing. So we have a relative min, since it went down and then up, at x equals 0. And you don't have to do anything else with that one. It doesn't have a relative max because those other 2 guys did not change signs. So they're not actually max or mins, they're probably points of inflection. If you ever question that, you can always go, remember, well, now you can't do this on the test, but if you're studying, you can go to Desmos and you can type in that function and you can see that those aren't maximums and minimums, they're points of inflection. So I'm going to do that real quick for us. And this function was 4, and then was it x squared minus 9, and then cubed. See right there at -3 and +3, those are just places where we momentarily flatten and we continue going down or up. And you'll see at 0, way, way, way down here. So it's crazy because this graph has extremely large values. 0 is it's not only the relative max, it's the absolute max, but we were only searching for relative extrema, which means we were using the first derivative. So down there is the lowest point at 0. So that is just a quick way to see if you know, when you're studying, are you doing those correctly? All right, let's talk about 12a. It says find the open intervals on which the function is increasing or decreasing. Again, if you're talking about slope of a tangent, if you're talking about maximums or minimums, if you're talking about increasing or decreasing, you're all usually using the first derivative. So let's take the first derivative of this. This would be f prime of x equals just x, because 5 divided by 5 would be 1 to the 4th, minus 9x squared, and then that would be nothing. We would factor out an x squared, and that would leave us with x squared minus 9. So we get x squared, x plus 3, x minus 3. And we're going to set that equal to 0. So the possibilities are 0, -3, and 3 again. We're going to do our chart with our first derivative to see if we have increasing or decreasing on each side of these. So we do -4, -2, +2, and 4. That'll work. Plug that into f prime of the number. So go here. I would actually plug it into the factored form. -4 squared is positive. -4 plus 3 is negative. -4 minus 3 is negative. So positive times negative is positive. -2 squared is positive. -2 plus 3 is positive. -2 minus 3 is negative. So positive, positive, negative. That's an overall negative. 2 squared is positive. 2 plus 3 is positive. 2 minus 3 is negative. So that means that's also going to be an overall negative. And then 4 squared is going to come out all positives. So when we look at this one, notice that we are increasing on -infinity to -3. I'm just kind of going above here, and 3 to infinity. And we are decreasing on -3 to 3. Since they're back to back, you can just say it's -3 to 3. You don't have to break it into 2 separate intervals, okay? All right, so let's look at what else I had marked on here. I wanted to do one of number 13, finding the absolute extrema. So remember, this is, you have to find the first derivative and find those critical numbers. Check to see if the critical numbers are even in the closed interval you are looking at. And then we do a test where we don't actually use the first derivative again. We say, let's plug our endpoints and any critical number in between them into our function, g of x. That will tell us the y value those points attain. The y value will tell you if it's an absolute max or an absolute min. Okay, so the first thing is to take the derivative. So g prime of x would be 3x squared minus 8x plus 5. This one we can try to factor. That's 15, and the factors again would be 3 and 5 to make -8. They'd have to both be negative. So 3x squared minus 3x minus 5x plus 5 set equal to 0. That is 3x, x minus 1, minus 5, x minus 1. So x minus 1 and 3x minus 5. So that is a possibility of x equals 1 or x equals 5/3. 5 divided by 3, is that outside of the interval? Yep, that's 1.6. So this guy right here is bigger than 1.5, so it's not working in our closed interval. So the only one we can test is 1. So when we go to make the absolute extrema test, you don't actually put the numbers on top there. You just say, okay, my smallest endpoint is 0, my only critical value in between them was 1, and my largest endpoint is 1.5. You are going to evaluate g of 0, g of 1, and g of 1.5, and obviously use your calculator if you have it. G of 0 actually comes out as 0. 1's actually easy to plug in. That's 1 minus 4, so that'd be negative 3, plus 5 would be 2. So 1.5 is going to need my calculator. So this would be 1.5 raised to the third power minus 4 times 1.5 raised to the second power, and then plus 5 times 1.5, which comes out as 1.875. So out of all three of these are ordered pairs, 0, 0, 1, 2, 1.5, 1.875. This one would be the absolute minimum at 0, 0. The absolute maximum is actually at our relative maximum as well. So our absolute max, and since it's a critical point, it means it's also a relative max, is at the point 1, 2. So yeah, it looks like she reported the Y values on those. That's not how it does it in WebAssign either, so I'm not sure why. We usually wrote them as ordered pairs. So stick with the ordered pair format because I want to do it consistently the way we did in class. Because it looks like she just reported the Y values on those. Okay, so the number 14 is approximate the critical numbers of the function on the open intervals shown in the graph. Determine whether the function has a relative minimum, relative maximum, absolute minimum, or absolute maximum, or none of these at each critical number. So to locate critical numbers, you're looking for maxes or mins that are, hills and valleys. So essentially, and even though it's not differentiable at a cusp, that is still a max on a small interval. So I'm noticing that at x equals 0, I have a relative max, because it's always the x value you reference, at about 3.4 maybe. I'm not sure what she wants you to do, 3.3, 3.4. So this one's at x equals about 3.4, because we're rough estimating that. We have a relative minimum. We have no absolute max or min, and there's a reason for that. The graph goes forever up this direction, forever down this direction. So if you're forever going up and down, you're not going to have absolute maximums and minimums. Okay, so on this one, at x equals 1, we have a relative max. At x equals -1, we have a relative min. At x equals 3, because that's this x value, we have another relative min. Now, both n values are always going up forever, so that means no absolute max. But the relative mins are the lowest this graph gets ever. There's no graph below this ever, ever, ever. So that means that this has, both of these are also absolute mins. Okay. So number 15, we're looking at B part because it was not on the answer key. That was pointed out to me by someone, so I want to make sure that we have this one so you can check it. So it says determine all the open intervals on the graph which the function is concave up or concave down and find all inflection points. So that means we need two derivatives, because to do concavity you need a second derivative. So we need to take the first derivative of h of x, which I'm going to rewrite h of x as x minus 5 to the 1/2. So h prime of x would be 1/2 x minus 5 to the -1/2, because we subtract a power, and we chain along the inside derivative, but the inside derivative is 1, so it doesn't matter here, but you can times the 1 if you need to. Then we'll do hx x, I can't speak, h double prime of x, which means we multiply negative 1/2 times 1/2, so that's negative 1/4, x minus 5, and then that would be negative 3/2 now. And again, the chain rule is 1. So I'm just going to rewrite what the second derivative tells us. So that is rewritten would be negative 1 over 4 square root of not square root. It's 3/2 now. Back up button. X minus 5 to the 3/2. Okay, so we do have a problem with the original function. Because this is a square root of x, there is a restricted domain here. X minus 5 has to stay greater than or equal to 0 for the domain of this function, because we cannot have imaginary numbers. There is no graph in that area. So that means all of the x's we can test have to be greater than or equal to 5. Now, if you plug in 5 down here, you're actually undefined here, but you're okay in the original function. So as long as it's okay in the original function, remember, it's something we can actually still do a test for an inflection point. So the problem is, when you go to do this, this is the only case where we don't have anything to test on the other side. So I kind of black it out. There is no function here, or h of x, I should say. Because if you plug any number less than 5 in, you're going to get square roots of negative numbers. So the only thing, this is the only time you can do a one-sided test. And what this is going to mean is that we're either completely concave up on the whole domain or concave down. And that also means there will be no points of inflection, because you can't switch your bowl if you don't have, remember, any spot to flip. There's no way you can change if there's not two different sides. So if we check 6 into h double prime, that would be negative 1 over 4 times 6 minus 5 to the 3/2. That's negative 1 over 4 times 1 to the 3/2. That's the square root of 1, which is 1, and then you cube it, so that's still 1. So that's negative 1/4. So that means this whole thing is concaved down. And usually we don't say equal to 5 because it's not really defined there, but when it's in the denominator, so we're just going to say 5 to infinity. And honestly, you're not really supposed to use closed intervals on talking about concave down and concave up. The bowl is on a open interval. And then there are no points of inflection. So that is that one, since the answer key was missing that problem. And remember, if you're looking for points of inflection, you have to plug your x value that you find is a point of inflection back into the original function, which is why there's a nasty point on 15a. But remember, you are to use your calculator for that, so don't try to do it by hand. So let's look at 16. So 16 says the function f of x equals x to the 4th plus 6x squared minus 16x plus 5 has a critical point at x equals 1. They're already telling you the critical point for this. Use the second derivative test to determine if that is a local max or local min at that specific value. So since they've given you the value they want you to test here, this is using the second derivative test, which normally we would have to take the first derivative ourselves, find all the critical points, and then plug all of them into the second derivative to see if it's positive or negative, which told us if it was concave up or concave down, which actually tells you whether or not it's a max or min. They only want us to check one of the critical values, so we can actually skip the critical value solving step, because they've told us just test x equals 1. So this is 4x cubed plus 12x minus 16, and then we take a second derivative, because we already know x equals 1 is an answer to that, and that would be 12x squared plus 12, and we want to plug 1 into that. So that's 12 times 1 squared plus 12. That comes out to 24, and 24 is greater than 0. Now, a lot of people will jump right to the conclusion that they think that means it is a maximum. It is not, because when it says if a second derivative tells you you're greater than 0, that means your bowl is concaved up, because that's what second derivative tells us. It tells us concave up or concave down. So if you're concaved up, you actually have a relative minimum at x equals 1, which is sometimes called a local minimum too, but relative minimum is what our book uses. Okay, so let's look at 17. This is the one like we did in class on our notes. It says, given the following graph of a function, y equals f of x, answer the questions about the function. So we have to locate the points that they're curious about. So at -3, that's this point right here, and at x equals 2, so that's this point right here. So we're going to talk about what is the graph doing at these two specific points. So it says, is f of x, that means the y value of the function, positive, negative, or approximately 0 at x equals -3. Well, if it was 0, it would be an x-intercept. If it's positive, it'll be above. If it's negative, it'll be below. So at this specific point, we have a negative y value. At the other one, we're above the x-axis, so we have a positive y value. F prime of x tells me about the slope of the tangent. At this yellow point, our slope of our tangent is going to be going downhill. So that means it is going to be a negative slope at x equals -3. At this point, the slope of my tangent is going uphill from left to right. So that means I've got a positive slope at that point. The second derivative tells me if my bowl is up or down. So at this point, the bowl is facing upwards. So that means we have a positive concavity. And at this point, the bowl is facing downward. So that means we have a negative concavity. The only time your y value can equal 0, that's like these, is if you're on an x-intercept. The only time your slope can equal 0 is if you're at the maximum or the minimum of the graph. And the only time your second derivative can equal 0 is when it's a point of inflection. So for us, or it's momentarily flat. So that is kind of where those would happen. All right, so let us look at the very last problem. This is the one that combines everything. It says the x-intercepts are not emphasized on the exam, but I always go ahead and find them because it's just quadratic formula if it doesn't factor. So I'm going to go through the whole shebang and give you every single piece of information. And I chose to do the polynomial one because the polynomial types are the ones that are most likely to be on the exam. We said we weren't going to give you one that has like a cubed root, which is what this guy is. So when we look at this, I'm going to do, let me write this down a little further. Okay. So the things that we're going to be looking for is we're going to be looking for, does it have x-intercepts? Does it have a y-intercept? What is a possible relative max or relative min? Does it even have those? Does it have a point of inflection? Okay. If it was like an x in a denominator, we would also ask, does it have an asymptote? So we're not dealing with those cases. So the hard part about these is usually finding the intercepts. Now, if you plug in 0 for all the x's, that's just going to give you 0. So the y-intercept is 0, 0. So I got that by doing 0 in for each x. If you're wanting to find your x-intercepts, you need to factor this. So that's going to be x can be pulled out. And that leaves me with this. We know that x equals 0. If we set that equal to 0, we're going to get 0, 0 for the x-intercept as well. But then we need to solve this to find the other two x-intercepts. So we're going to kind of come over here and do quadratic formula because it doesn't factor nicely. So x equals -b, so that'd be +9 plus or minus square root -9 squared minus 4ac all over 2a. Okay, so -9 squared is 81. So square root of 81. That's negative times negative, so that's going to be positive, and that's 8 times 90. That's plus 720, I believe, over 2 times 2, which is 4. And then you just need to add those two guys together. So that's 9 plus or minus the square root of, that would be 1, carry the 10, 801. Yeah, and then that's all over 4. So we don't care about anything but getting the decimal approximations here. So square root of 801, and then I'm going to add that to 9, so plus 9, and then divide by 4. That gives me 9.3. So one of my x-intercepts is 9.3 comma 0. And then I'm going to do the subtraction case. So 9 minus 801 square rooted, and then divide that by 4. That's negative 4.8 comma 0. So that's the algebra stuff. That's the stuff we would have taught you in 136. Everything else we find using calculus. So to find the relative max and min, we need the first derivative of this guy. So that would be f prime of x equals 6x squared minus 18x minus 90. I believe we can pull a 6 out of that, so that'd be x squared minus 3x. Is 90 divisible by 6? Let's hope so. Yes, 15. So minus 15. We can set each of these equal to 0 when we factor it, so that's x minus 5, x plus 2. So it looks like 5 and negative 2 are the two critical numbers. So we make a chart for those and test the first derivative test. So negative 2, 5, put them in order from least to greatest. So I'm testing negative 3, 0, and 6 into my first derivative. So you can go right here. This is going to be negative 8 and a negative 1. So two negatives multiplied together make a positive. 0 will make negative 5 and 2. And of course, there's a 6 out front, but it's positive. So that's going to make a negative. 6 minus 5 is positive. 6 plus 2 is positive. So that's going to be a positive. So increasing to decreasing means that this guy is a max. Decreasing to increasing means this one is a min. So we have a relative max at an ordered pair that I haven't found the y value of yet, and 5, 0. So here's where you have to go back to your original function. We need to evaluate f of negative 2 and f of 5. Just writing it down up there so I can remember what we did. So negative 2 cubed is actually negative 8. You have to be careful with that. Times 2 minus 9 times negative 2 squared is actually 4. And then negative 2 times 90 is going to be positive 180. So 128 is the y value that we get there. For the minimum, we have to plug in 5. So 5 cubed times 2 minus 9 times 25, because it's 5 squared, and then minus 90 times 5. So negative 425. So notice that is very negative. And then I got 425. I think, was there a typo on the answer key? Oh, no. She had that on the answer key. Those didn't factor nicely. Because I'm double checking that as we go. Did I improperly do my derivative? Let me double check real quick. So 2 times 3 is 6, x squared minus 18x minus 90. If we pull that out, we get factors of x minus 5. Oh, that's why I messed up. Sorry. I did mess up. I knew something didn't look right when I then jumped in. 5 times 2 is 10. Obviously, when it's late, you should not make math videos. So this doesn't factor. That was mean of her. Okay, so I've got to rework these. I'm close, but they're not the right answers because this does not actually factor. So we have to use quadratic formula again. Yay for that. So x equals negative b plus or minus square root. B squared is 9 minus 4ac all over 2a. So that would be, I mean, the test is going to come out the same. We just had we were slightly off on our values. So that is 4 times 15. So that's 60 plus 9. So this is 3 plus or minus the square root of 69 over 2. Square root of 69 plus the 3, and then divided by 2. That's the 5.65. So one of them is 5.65. So 5.65. The other one is negative 2.65, I believe, but let's double check. So 3 minus the square root of, nope, not 3. 3 minus 69 square root, and then divided by 2. Yeah, negative 2.65. All right, so because those are so close to the answer I had a minute ago when I improperly factored, you will notice that the test is going to give us the same results. That would not be true if they were way off the originals. Okay, so this is, again, negative 3, 0, and 6. Plug it into the first derivative, and then that is going to be, I might as well just show my work on those. 0 is going to be easy. 0 is negative because it's just going to be negative 90. If we plug in negative 3, that's going to be 9 times 6 plus 18 times 3, because that would turn positive, minus 90. So that's positive. If you do 6, that is 36 times 6 minus 18 times 6, and then minus 90. So that's also positive. Okay, so still this relative max happens at negative 2.65, and the relative minimum happens at 5.65. So because that didn't factor the way I thought in my brain, they're actually decimal answers. So we do have to plug those back into the original, and just to save time, you guys can see it on the answer key. When you plug in the negative 2.65, you get 138. When you plug in 5.65, you get negative 435, and that's plugging it into the original function. Okay, to save time, we're going to do the point of inflection next, so I need to take a second derivative. So let me scroll down a little bit, because we still have to graph this. That's why there's only one of these on the test. So f double prime would be 12x minus 18, so set that equal to 0. That is, divide both of those by 6, that's 3/2. Now we don't know if that's a point of inflection until we do the concavity test. So we need to put a value on each side of 3/2. So we could use 0 and maybe 3. Plug them into the second derivative. 0 gives me a negative, 3 gives me a positive. That means that is a point of inflection because it changes concave down to concave up. Okay, so this would be 3/2, comma, and if you plug it into the original function, you get negative 148.5. So I wanted to save some time so we could actually see how this graphs. All right, so first step is to plot all of your intercepts and obviously label out your graph how you're counting. So I'm not going to be able to look at all these at the same time because I am out of space. But the biggest my x-intercept get is almost 10. The smallest my x-intercept gets is about -5. So I need to maybe count by 2s on my x-intercept axis. So we're going to say that we're counting by 2s. So 1, 2, 4, 6, 8, 10, -2, -4, -6, -8. And then we're going to have to count by something extremely large on our y-axis because we get all the way down to -435 and we get as high as 138. So maybe I'm going to count by 50s. So it's good to mark this so your teacher knows what you're doing. So 50, 100, 150, 200, 250, 300, 350, 400. I need more space. Let's make this better. I might make it a little smaller. You could also count by hundreds. That would be another option. So let's do 50. So 50, 100, 150, 200, 250, 300, 350, 400, 450. So I counted by 50s. Okay. And then -50, -100, -150, -200, -250, -300, -350, -400, -450. That's just because you have to stay consistent on the y-axis and then you have to be consistent on the x-axis. So 0, 0 is my first point. 9.30, so that would be almost, this is 8, this would be 10, so that's going to be a little over half. I'm going to do these in red so we can see them. Okay, and then -4.8, so -2, -4, almost -5, so that's going to be about here, almost halfway between -4 and -6. And then we already had the y-intercept because that's the same as the x-intercept. We need to plot a relative minimum of 5.65 and then -435. So 5.65 is 2, 4, 6. So 5.65 is going to be about here. And I did all the way down to -450. So that's going to be a little bit in between -400 and 450, almost half. And then I always mark that that's the min. So I know that that's the lowest that I get on this little piece. And then -2.65 is about right here. And then we go up to 138. So 50, 100, 150. So it's about somewhere in here. And again, we're doing a rough sketch since the numbers are so large. And then, so that's my max. And then I have a point of inflection at 1.5, which is not even, this is 2, so it has to be somewhere in between there. And down at -148. So 100 is here and 150 is here, so almost at that. That's my point of inflection. Remember, we were concave down on the left side of the point of inflection, and we were concaved up on the right side. So there is my graph, the best that we can do with, what we had to work with. So this is, the big problem on the test. So just make sure you take your time. Don't do silly things like I did where you factor something that's not factorable. Make sure you know your quadratic formula. So I'm going to post this video right now, and I'm also going to type you guys up a little kind of like a quick study guide. You can just remember what are the procedures that we do for every important thing. All right, I'll see you guys tomorrow.